looking at here, right, is the end of hopefully chapter 13. Now, yesterday we spent pretty much going over all the stages. Now we get to do the whole thing from start to finish. So question 13 talks about a story with cars and how flat or how much pressure there is on the tires. And so what they got here is, let's see. I'll just read it out to you. It saves me jumping back and forth. An earlier exercise posed the following research question. Many cars have a recommended tire pressure of 32 psi's. At a roadside vehicle safety checkpoint, official randomly select 70 cars. So I'm writing down N equals 70. And they wanted to know whether drivers on average had too little pressure in their tires. So they've just said too little pressure. So that becomes, they want to prove that mu is less than 32. So I've written that down there. And so they got these 70 cars, and they found out that the mean pressure for them was 29.5. And they should have told me, and I'm still reading for it, what the standard 3 and the standard deviation is 3. So now I've got all the numbers. Let's do a hypothesis test on it. So they told me it was 70 vehicles they stopped. The average tire pressure was this. The standard deviation was that. And they wanted to see if this is enough evidence to prove that people actually tend to blow up their tires to less than this, the safety limit of 32. So they also gave me a significance level of 0.05. So that's basically the info. So first thing I'm going to do is set up the null and the alternate. And I've already put the alternate down. I know that that's the alternate because in the story they said they'd like to see whether they could prove it's less than 32. Are you happy that the null would be equal to 32 then? Okay, that's pretty good. Next thing I'm now going to do is I'm going to get the test statistic, in this case the t-score, right? So that means I have to do a number of things. First thing I'm going to have to calculate is the standard error, which is that guy, which is 3 over the square root of 70. And here we go. 3 divided by square root of 70 is nothing 0.35. What do they want? They want 2 decimal places, so I'm going to go 3586. So I'm working on that, as we said yesterday. Even if they want to always do all your working to 3 or 4 and just round, the final answer to, in this case, 3. So I got the standard error. The guy they're calling the test statistic is basically the t-score. And we get that by taking the mean of the sample, take away a guy called mu naught, divided by the standard error of the sample. And the mean that we got was 29.5. Mu naught is this guy. Okay, so whatever number is there, that's the mu naught value, right? It's also called the null value, right? If you want to know another name for it. So in this case, that's going to be 32. And the whole thing's going to be divided by this fella. And on my calculator then, little bracket, 29.5, take away 32, close the brackets, and divide it by 0.3586, and I get the number negative 6.5. 0.97 because they wanted it to do decimal places. So you notice it was here that I did the rounding off, not anywhere else. So we got our guy, our test statistic. Now, after the test statistic, we can get our p-value. And our p-value is the probability that we get a t-score less than this number. We know it's less than because the alternate is a less than story. And we use this t statistic, and that always goes there. And this is where salt comes in. So I'm hitting the salt button, and let's show you what that looks like. Now, in this particular case, it's exactly where it needs to be, right? Inferential statistics, one sample t, right? So I don't need to change anything. This is 0 and 1, so I won't change anything there. The sample size, why are they doing that? Change that. They didn't put it in the right place. It should be in distribution with t-score. There we go. That was an easy mistake. Show you what I did. You know how similar it looks? I mean, superficially, you can easily be in the wrong place. But I know this is the right place because it's got left, right, and both tails. And that's where you want to be, right? The one that has left, right, and both tails. T-distribution, degrees of freedom. This particular one had 70 numbers in the sample, so that becomes 69. We are trying to prove that it's less than, that's left tail, less left, that works. And this number in here is going to be negative 6.97. And don't worry about the warning sign, it just means that this answer is like 0.4 zeros and a 1, right? It's so close to 0, you can't really tell the difference. So we've now got our p-value. It's a really nice small number, essentially 0. So let's do our test. The next phase is you ask yourself, your test, is your p-value less than the significance level alpha? In this case is 0 less than this one. And the answer to that is yes. So what we can do is basically pick from a set of 4 choices, and then you can do your conclusion. So let me show you what that looks like when you're doing your homework. So we just found out our p-value was 0, and we did our test. And on the basis of this number, what conclusion can we make? Well, if your p-value is less than alpha, doesn't that mean that the alternate is true? But there's different ways you can phrase the alternate HA is true. You reject the null hypothesis is another way of saying the same thing, right? Rejecting the null hypothesis is the same thing as accepting the alternate. And we can conclude then, that on average, drivers have too little pressure in their tires. Any problems with that? I'm hoping that as we keep kind of battering this poor dead horse, dead donkey, that you'll just get used to the process and it'll become a little bit more comfort, right? You won't be so freaked out by all the things that you have to do because you do the same things every single time, right? So next story, moving on. So this one, am I doing this cell story one? or the herd the cow. Let's do this one, 14. This is the cell phone story. A cell phone company knows that the mean length of calls for all of its customers is 9.4 minutes. Okay, the company's thinking about offering a senior discount. I've heard that story before, and they're getting that because they tend to not use their phone for so long. At least that's what they hope. The only way to identify seniors is to conduct a survey and ask people whether they're over 65. Okay, that makes sense. Using this method, the company contacted a random sample of 100 seniors. So I finally got a number I can write down. Sample size is 100. And they took, on average, their phone calls were 8.5 minutes. And their standard deviation was 10 minutes. Got a big variation there. And we want to know, can we prove, is there evidence that seniors use the phone on average less than that initial number, and that was less than 9.4 minutes. And the significance level here is 0.05. So it might have nothing to do with tire pressure, but we're going to treat this pretty much the same way we just did that one. Right. So I'm going to start with my null and alternate hypothesis. Right. In this story, you're trying to prove, right, that the average, right, is less than 9.4. So the null hypothesis is it's still 9.4 for seniors. What's the alternate? What are you trying to prove?
Mu is less than 9.4.
Right. So it's very similar to the tire story, isn't it? It's another one of those prove it's less than something. Does that make sense in the data? Yeah, they do 8.4, this is 9.4, right? So we get the standard error, which is going to get me my test statistic. So the standard error of X bar is S over the square root of N. It's 10 over the square, oh, I wish numbers were like that all the time. Could do that one in my head, the answer's 1. It's very nice, but kind of unrealistic. And so we get our test statistic. Essentially what we call our t-score. And it's X bar, taking me mu naught over the standard error. It's 8.5. Take away mu naught. This number here is mu naught. And that's pretty easy calculation, I believe. But it's negative 0.9, but let's be absolutely sure. Negative 0.9. So far, so good. So what do I do now? I get the p-value from salt. And in this case, p-value is going to be the probability that you get a t-score bigger than this number, less than this number, or just different from this number. So what's it going to be in this story? The t from salt is less than negative 0.9. We'll go for that one. If you're saying, how do you know it's less than? Remember, whatever that is, this is the same, right? If that's a greater than, this is a greater than. I'm going to just hit Salt and do it for you, so you just bear with me. So I'm on to distribution. I'm going to hit T-distribution. Degrees of freedom this time are 99. And the T-score is negative 0.9. And the p-value I got here, noticeable, is 0.19. So now I do our test. Our test is our p-value less than significance level alpha? Is our 0.19 less than 0.05? In this case, the answer is no. And when you get a no, there are various sentences that you can use, but the most common one would be something like this. There is not enough evidence. To reject H0. And that is pretty much the end of that question. Any questions about that? Are we getting a theme? Are we getting a flow to how these stories work? If you understand the flow, you can put any question you could possibly want and prove it, or show that there's not enough evidence, because it happens as well in every case. So where are we going this time? I do a Cal one, try to judge it. Yeah, Cal one sounds good. In question 15, a herd of 1,500 cattle was fed a special high protein grain diet for a month. It's probably expensive as well. A random sample of 30 cattle was weighed and gained on average 7.3 pounds. And the standard deviation was 5.3 pounds. And we are being told, so we didn't even need to ask or figure it out ourselves, we're being told that the null is that it's 7, and that the alternate is that it's bigger than 7. Okay. We already know that the mean is that, and that they picked 30, and the standard deviation is 5.3. So I just read through that story and I picked up all the usual culprits, and the significance value is going to be 0.5, right? If you get a question where they just don't tell you or they forget to tell you, assume that it's 0.05, because that seems to be their go-to number, right? Just in case there's one that misses it. And they jump right into it. The first thing that they ask you is find the T-score. Find the test statistic. So step 1's done. I'll find the standard error. Which is that guy. And 5.3 divided by the square root of 30 gives me 0.967. This guy you get from that formula. There's your mu naught. So it's going to be 7.3 take away 7 divided by nothing 0.967. going to get a 7.3, take away a 7, divided by 0.967. And the answer I get is 0.310. So that is question A. Get the t-score. Then they ask you to get the p-value. So it's going to be the probability that you get a t-score greater than, right, because of that, this number. Same thing every time. Now I'm just going to do it off screen. Degrees of freedom, right? There are 30 in my sample. What number is my degrees of freedom? Just to remind you.
29.
29. And the other stuff, it's a greater than, so it's a right-tailed test, and it's to be greater than 0.310. And the answer I get is a rather disappointing 0.38. So p-value. It's that bit done. Now, let's do our test. Is our p-value less than the significance level of? Is 0.38 less than 0.05? And the answer here is a big fat no. So let's show you the choices that you're going to make based on that. We have checked the p-value and it's not less than the significance. Doesn't that mean there's not enough evidence to reject H? No, right? That's the basic answer. So we would reject a no. Nope. We would fail to reject it. Okay, that's the way of saying that. This means on basis of the evidence, you cannot conclude that the mean weight gain is more than 7 pounds. Are you okay with that choice? Each one will be in its own little world. Any questions so far? Are we good? Okay. Basically going through each one. We've got what, 2 to do. That's it. In question 16, the average height of children who are 2 years old is 34 inches. Okay, so you've just told me that the null hypothesis is 34. A random sample of 35 children. So you've just told me my sample size is 35. And their average height is 29 inches. And that the standard deviation is 1.8 inches. The researcher is suspicious that children at a daycare are not growing as quickly as they should. So that is, he thinks there's evidence to prove that it's less than 34, which seems reasonable. Do you agree? I have no idea why children in the daycare do not grow as tall as children who don't go to daycare, but evidently that's the evidence, at least in front of us. We are now going to go through the entire process. They just give you little snapshots. Their snapshots are, they want you to find a test statistic, they want you to find p-value, and then they want you to do the conclusion. So that's a little snapshots in the way. So we've already set up the null and alternate. Let's go for the t-score. A standard error is given by that, which in this case is 1.8 divided by the square root of 35. And go over here and I do a 1.8 divided by the square root of 35, and the answer I get is 0.304. So I can now get the t-score. It's the mean takeaway mu naught over the standard error. That is your mu naught. In this case, it's 34. So we have 29 take away 34 divided by 0.304. And on my calculator then, 29 take away 34 divided by 0.304. And the answer I get is, wow, is negative 16.45. Can I get it? That's essentially part 8 done. Right, let's find our p-value. It's going to be the probability that you get a t-score less than this number. I already know what the answer is going to be, and I haven't got it in front of me, and I haven't done SALT. What do you think the number is going to be for a t-score like negative 16.45? Exactly.
0, pretty much.
Pretty much. So can we trust? I know it is, right? So we did that bit. We're good to go. T-scores are very like Z-scores. You know, like by the time you get to 3 and negative 3, aren't the answers going to be almost 0, right? Very tiny. Only difference is that T-scores tend to be a little bit bigger, right? So you can get a T-score of 4 and 5. Then you're pretty sure that it's going to be 0. So conclusion. So basically that's part B done. Is the p-value less than significance level alpha, which is in this case 5% again? Well, is 0 less than 0.05? The answer is yes. And let's show you yet another version of how they write down the conclusion. See, there's not just one way of doing it. Right, haven't we proved that there's enough evidence, right? Our p-value was less than 0.5. So, do you accept the null? No. Do you fail to reject the null? Do you reject the null? Or do you reject the alternative? Now, which one of those 4 is the right one to pick? And I see 3 fingers, and that is right. So you can reject the null, you can accept the alternate, right? Same thing. You can fail to reject the null, right? That's another different situation that could happen. And we are now on to this story. It's our last question. It's quite a long one. I'm only going to do one piece of it. But it has been hypothesized that the mean pulse rate for college students is about 71 beats per minute. So somewhere someone has figured out that it should be 71. Okay. A sample of university students recorded their gender and their pulse rate, and assume that the sample is representative of all male and female university students. So what we've really got here is not one hypothesis test, but 2. If you look at the females, there were 34 of them, and their pulse rate was 76.8, and this is the standard deviation. And then for the males, there were slightly more of them. The mean is this one, and the standard deviation is that. And in question A, we're going to find the test statistic. Can you remember what the test statistic is code for? What's it another name for?
Z-score.
right? In our case, a t-score, right? T-score. Right? And you'd go and you do it, and you do a p-value and a conclusion. And then you would do it for the females, and you would write down the t-score, the p-value, and your conclusion. But since I'm only going to do one of them, let's look at the data and see which one I'm going to pick. Well, we're trying to prove, right, that it's right. Let's say I'm trying to prove that the numbers are for the female and the males, that they're different from 71. There's no indication that it's greater than or less than. In fact, if I'm doing it for the females, isn't there evidence that it's more than 71? But if I was doing it for the males, isn't there evidence that it's actually less than 71? Now, since they haven't mentioned either, that's why I had a kind of hesitation to look. I'm just going to go for the blacks, you know, the bog standard, that it's not 71, right? That it's different. And in one case, it's bigger, and the other, it's probably smaller. So let's do the females. I think there is more evidence, if there's going to be any evidence at all, to prove that it's not 71, right? It's different. It's going to come from the female data. Why do you think that one is likely to be significant rather than males? Is there any clues in the data that would make me think that would be the reason?
Means a lot larger than it than the males is.
Yeah, would you agree that the female is quite a bit different, right? If you're looking for evidence, shouldn't they be as far apart as possible, right? That's where you're going to get the evidence. So that's the one I'm going to pick. So I'll nip over now and we'll set this question up. And this is essentially the last time that you're going to see one of these. So the null hypothesis is that it is 71. And I've decided that the alternate is going to be that it's different from 71. For the women, this is the one I'm choosing, the sample size was 34. The standard deviation was 11.5, and the mean of their heartbeats was a 76.8. Significance level is 0.05. Right, that's all the information I now need. So here goes. Calculate the standard error first. What do we get? 11.5 divided by the square root of 34. And I get a 1.97. Okay. Our t-score, what they call the test statistic, is given by that formula. That number there is mu naught. So it's going to be 76.8 take away 71 divided by 1.97. On my calculator then, 76.8 take away 71, all divided by 1.97, and the answer I get is 2.94. Things doing okay? Let's get the p-value. It's going to be the probability. Now, If that was greater than, I'd be looking at greater than 2.94. If that was less than, I would be looking at less than 2.94. But since that's a not equal to, we get the weird one, which is basically you want t to be less than negative 2.94, or you want t to be greater than 2.94. And that we call a two-tailed test. And I'm going to show you what that one looks like on Sol. Let's see what we get here. So the two-tail is by far the ugliest one to deal with. But let's see if I can shrink this window up so you can kind of visualize it. Here we go. Now, both tails. That's why it's called two-tailed, right? T-distribution. There was 34 numbers in the data, so the degrees of freedom are 33. I want it to be less than negative 2.94. And on the other side, I want it to be bigger than 2.94. So you use the same numbers, one plus and minus, one bigger, right, one less, going like that. And we have got a p-value here. So the answer is 0.00595. You want to do kind of overkill. Are you comfortable about how you do a two-tailed? It's a little bit messier than everything less or everything big. It's a kind of both at the same time. And now we come to conclusion. We do our test. We say, or we ask, is our p-value less than the significance level alpha? Is 0.00595 less than 0.05? Is that true? Yes or no? Right, that's tiny, like a lot of extra zeros, so the answer is yes. And when the answer is yes, don't you have to do lots of variations of how you say that, right? One is, isn't there enough evidence to prove that it's different, right? That would be, if I phrase it that way, and we'd say there's enough evidence. To accept the alternate hypothesis. Right, so I could do it that way. Couldn't I do enough evidence to reject the null hypothesis? That's the exact same thing, just phrased in a different way. Couldn't I just say in English, there's enough evidence to prove that women's heartbeats are not 71 on average, right? They're different. In this particular one, is the hypothesis in the same one in which a decision lead to an action is required? Well, it's a kind of weird one, but whatever. Any questions? The last time we're going to do one of these unless we do it as a revision thing. So this is your chance. If I don't understand how you got from here to here, or how do you do this again? What do you mean? Whatever it is, this is your chance to ask. I'm getting nods. Good. You're going to have to take what I've done and turn it into English. Turn it into something that makes sense to you. It doesn't need to make sense to the next person. You just have to figure out how to write down all of this, right? You know, I do it like step one, step two. You might write it down some other way, but whatever it is, you've got to figure a way of making this stick.